Good morning, Sarah. I am so sorry that this is so late. Um, it's been a crazy week. Let me, um, let's work through some practice ones here. So this is on the practice pedigree problems spreadsheet that I sent out. You're welcome to go work through these. I'll only work through a few of them just to help you think through these. I tried to put together a flow chart. I'm not good enough at them yet to have done a very good job at it, so I'll try my method and see if I can help you walk through it. And I apologize for not having a flow chart ready for you. But I'll show you this way and hopefully it still works. I have a 4-step process. And if you do the 4-step process, you should nail it every time. 1, step 2, step 3, step 4. Okay, here we go. So step 1 is the one that you already know how to do. It's determine if it's Y-linked or mitochondrial. Basically, we're trying to eliminate them. And the reason why I start with these is because they're obvious. Like you were mentioning earlier, these ones are obvious to see. If the pedigree is Y-linked, you know it right off the bat, and you don't have to waste your time with the other ones. If it's mitochondrial, it takes a little bit of investigation to double check to make sure it confirms all of the rules of mitochondrial, and then poof, you know it's mitochondrial, you go on. If you check here, in this case, this one's not Y-linked because there are women affected, and it's not mitochondrial because I have a man passing it to children, and the women don't give it to all of their children. So both of those disqualify it as mitochondrial. So out of my 6 on my list, I've got autosomal dominant, autosomal recessive, X-linked dominant, X-linked recessive, Y-linked, and mitochondrial. By doing step 1, we've eliminated 2 of those and gotten down to 4 possible options. Okay, step 2 is determine if it's dominant or recessive. And the little rule of thumb for this, again, it doesn't always work. Sometimes recessive ones look like dominant ones, and I'll try to help you figure out or catch those ones when they do come. But dominant or recessive, the rule of thumb there is that if it is in every generation, then it's dominant. What we mean by that is if every affected child has an affected parent, if every affected child has at least one affected parent, then we consider it most likely dominant. If there is ever anywhere an affected child that has 2 normal parents, that has to be recessive. Does that make sense? So in this case, the reason why I phrase it that way is because a lot of times when we say recessive genes skip generations, people see something like this on the far left here and say, aha, it's recessive. That's not skipping. And that's why I've tried rephrasing it. Skipping means you have to land again. It means you jumped, but you have to land again. In that case, so far as the pedigree has told us, there's no landing. It just disappears. So we didn't vanish for a generation and then come back again. We just vanished. That's different. That's not skipping generations. That is just inheriting recessive alleles and marrying a spouse with recessive alleles and passing that on. So that's disappearing. That's not skipping. So that doesn't disqualify dominant. And in this case, then, every affected child has an affected parent. That one has that one has that one, and these guys all have that one. So in this case, this meets the rules to be most likely dominant. Now, if we go to step 3 then, so by determining that this one is dominant, we have gotten rid of 2 more. It can't be X recessive and it can't be autosomal recessive because we just narrowed those out by declaring it dominant. So now we're down to 2. We've got autosomal dominant and X-linked dominant. Step 3 is to determine if it's autosomal or X-linked. There's a rule of thumb there, and then I'll get into a little more detail. The rule of thumb is if you count all of the affected women and compare it to the number of affected men, if they're relatively close to each other, it's autosomal. If they're pretty far apart in that one generation or one gender seems to be far more affected in this pedigree than the other, it's usually X-linked. For example, in this one, I have 1, 2, 3, 4 affected women in the whole pedigree. Then there are 1, 2, 3 affected men in the whole pedigree. So that's a 3-to-4 ratio, which 3 and 4 are relatively close to each other. It doesn't have to be spot on right down the middle. 3 and 4 are relatively close to each other. If they're getting to about 2 apart from each other, like if it was 3 and 5, that's starting to be on the tilting line between autosomal and X-linked, and in there you're just going to have to make a call, and there are some other things I'll give you in a sec here. But in this case, given that they're relatively evenly affected, then that seems to say it's autosomal, because if you remember on an autosomal Punnett square, if you remember on an autosomal Punnett square, all 4 squares apply to both genders, meaning that both genders have the same chances of inheriting the disease as the other one. With X-linked, however, each gender got only half of the pedigree, which changed their chances, or which made it more often than not different odds for a daughter and a son to get the disease from the same couple. So you're going to wind up with a lot more daughters or a lot more sons involved. So that's kind of the rule of thumb. And again, it doesn't always hold up, but here's the way that you can tell, especially if we did an X-linked recessive one. Here's things to look for. For X-linked ones, holy cow, why is that so tiny? Increase the size of my little rules here. Okay, here we go. These are the X-linked things to look for. The X-linked things to look for are, do men pass it to their sons? If affected men give it to their sons, it cannot be X-linked, because if you do a Punnett square, men don't give an X chromosome to their sons. They give a Y chromosome, and a Y chromosome is not an X chromosome. So an affected father, if he passes it to a son, all X-linked things are out the window. It has to be autosomal. Autosomal is kind of like the bottom of the totem pole. If X-linked gets disqualified, then it's autosomal. Or if it seems more balanced, it's autosomal. Otherwise, if you can't prove X-linked out and it looks reasonable to be X-linked, it's X-linked. So, because every X-linked one could potentially be autosomal as well. So we're just looking for the most probable answer. And in this case, so here are the things to look for on X-linked. First off, I guess we'll remember these here. That's right, I gotta upsize these two. Okay, there we go. Number 1. So if affected men pass to sons, no go. Affected men cannot pass it to sons. Number 2, underline this here. Separate all this. Okay, there we go. Number 2, if it's X dominant, so X dominant, then an affected father must give it to all of his daughters and none of his sons. Because remember, the affected father is going to give his X chromosome to both of his daughters, or to both daughter Punnett squares, so all of his daughters. And if he has the dominant allele is the disease, then all of his daughters will show it regardless of what their other X is. So if it's X dominant, every affected man must give it to all of their daughters and none of their sons. Trying to think what the other trick is. Maybe those are the only two. Sorry, I'm tired this morning. Let's see. Oh, here's the other one. For X-linked recessive, every affected daughter must have an affected father. Reason for that is because if you're X recessive, or if the disease is X recessive, what's the only genotype a female can have to show the disease? They have to be X little r, which means they had to get an X little r from mom and an X little r from dad. But if dad, since he only has one X, if he has an X little r to give to his daughter, that means he has to show the disease as well. So that's where my skipping generations thing falls through, is on X recessive, because every affected daughter is going to have an affected father. They have to. They absolutely have to. The mother would have to be at least heterozygous, if not better than that. But the father has to be affected, and that's the trick. So in this case, on this pedigree, there's a number of things pointing towards autosomal, and I can check through each of these. So there's the rule of thumb, which says they should be, if it's X-linked, I should have a lot more women than men affected, or a lot more men than women affected. And in this case, I've got 4 women and 3 men, and so that's about balanced. So that rule of thumb says autosomal. Then if we check my other rules here, if the affected men pass it to sons, it's a no-go. I've got an affected man passing it to a son. It's a no-go. If X dominant, every affected man must give the disease to all of his daughters and none of his sons. In this case, I've got an affected man who gave it to 2 of his daughters, but not the third one. So again, it's a no-go. And X-linked recessive, every affected daughter must have an affected father. And in this case, there's an affected daughter without an affected father. So if any of those 3 rules are violated, it can't be X-linked. And in this case, we happen to violate all 3 of them. So this one is pretty solidly autosomal dominant, because we've got no children, or we have no children of parents that are unaffected with the affected child, no affected children with unaffected parents. And it violates all of the rules of being X-linked. So that has to be autosomal dominant. Does that make sense? So notice how I aimed to eliminate X-linked, because that was the more complicated one, and autosomal is kind of a catch-all. If it's not X-linked, it's autosomal. So then, because we threw it out as X dominant, the only option left on our list is autosomal dominant. And if we check that with my little answer key, there it is. Does that make sense? Let's try a little tougher one here. Number 2 is a little more tricky. Ooh, let me bring over my rules here. Way the heck over there. There we go. All right. So on this one, we have our three rules. We have y-linked. So we have the first three rules. I'll add the fourth one here. I realized I didn't hit the fourth rule. That's funny. Okay. Y-linked or mitochondrial. So if we bring our options back here, autosomal recessive, X dominant, X recessive, Y-linked, or mitochondrial. Okay. In this case, it's not Y-linked because I don't have an affected father giving it to all of his sons. And it's not mitochondrial because affected fathers, although they aren't giving it to children, you have children that are getting the disease from non-affected parents. So that can't be it. Plus, it's a dad giving it to his daughter. So this can't be mitochondrial. So we just ruled out the first two. Okay. Dominant or recessive. This one's tricky because I did a trick here that you'll never see on a real exam where the in-law is married. Always watch the sticks to figure out who is child and who is in-law, because she is an in-law, not a child. There's not a vertical stick there. So in this case, we have a man giving it to nobody, and then poof, it reappears. So in this case, it's possible to be a dominant one, but very unlikely, because what are the odds that a man, even if he's heterozygous, would have 6 children and with a 50-50 chance flip tails every time? So and it can't be X dominant, but we'll get to that here in a sec. Okay, so dominant or recessive, this one looks recessive because here we are skipping generations. Again, this one's a little trickier than they should be. We're skipping generations here. Now we go, so we have ruled out X dominant and autosomal dominant. Now in this case, we check. This one's kind of a tougher ratio because we've got 2 men to 1 woman. So it's like, okay, the rule of thumb doesn't really help us here. Let's check the rules. If affected men pass to sons, it's a no-go. Do I have any affected men giving it to sons? No. So we're good on rule 1. If X dominant, every affected man must give the disease to all of his daughters and none of his sons. That doesn't happen here. So it can't be X dominant. Let's look to see if it's X recessive, because that was one of our options anyway. If it's X recessive, every affected daughter must have an affected father. We only have one affected daughter here, and she has an affected father. Does that make sense? So in this case, it meets it kind of botched my rule of thumb, but it met all of the rules that it needed to, because we weren't considering it for X dominant. So I guess it doesn't need to meet all 3 rules now that you mentioned it. It just has to meet 2 of them, as long as number 1 is affected or is included in one of those 2. It's like Emperor's New Groove. It will be the 3 of us, soon to be the 2 of us. And I'm one of those 2, right? Sorry, that was spontaneous. Okay, so in this case, autosomal recessive is not, this couldn't be autosomal recessive, but it's more likely X recessive because it meets all of the rules for X recessive. So we call this X recessive. And this will be really embarrassing if I'm wrong. Okay, sweet. So that's starting to make a little more sense. Here's rule 4. Rule 4 isn't necessary, but it will help you feel more confident about your answers and not get caught in traps. Rule 4, because remember, rules 1 through 3 gave us the answer. Rule 4 is double checking you didn't miss something. And the way that I like to do that is defend yourself. Assume you're right and come up with a story to prove it. So here's how I do that. I'm assuming, because remember on the exam, I'm not going to have something telling me if I guess right or not. I'm assuming I'm right with X recessive. I've got a man with, if it's X-linked recessive, what does his genotype have to be? Because he's affected, so he has to be X little r Y, right? Because that's the only way he can be affected. Woman here, I don't know if she's X big R, X little r, or X big R, X big R, but either way, it doesn't matter. Plus, it's more likely if she has X big R, because that would mean all of their children would be more likely not to have the disease. So it doesn't matter what you make up here, as long as it makes sense. So I'll put X big R simply to help make my point stronger. So if you run Punnett square, this son here will get an X big R from mom and a Y from dad. He won't have the disease. That's good, because that's what I claim should be happening. If we come over here to him, same story. Gets an X big R from mom and a Y from dad. That's good. It's behaving like it should. This daughter will get an X big R from mom and an X little r from dad. That's good. It's behaving like it should. X big R, X little r. That's good. X big R, X little r. That's good. Okay, now I double check this one here. If I have a man that's affected, he has to be X little r Y. And if I have a, so then this son can get an X big R from mom and a Y from dad and not be affected. Same story here. And this daughter gets the X little r from mom and the X little r from dad, and poof, she's affected. X little r, and then this daughter gets an X big R, X little r, and isn't affected. And then these guys out here, they marry X big R wives and have no affected children. I just proved myself right. There was no catch in my plan there. Let's assume I went blind on this one. Let's go autosomal dominant. Autosomal dominant, let's pretend that I had guessed it was autosomal dominant. Oops, I always pressed the wrong button on that one. There we go. So we'll back this up here. Let's assume I thought it was autosomal dominant. Actually, that's a terrible example because autosomal dominant is possible in this. Well, yeah, okay, let's actually use it here because this will be good practice. Okay, if it's autosomal dominant, then he has to have at least one big R, and a little r is because he also has to have a little r because all of his children have to come out little r, right? So they're going to have to be little r. Oops. And she has to be little r, and little r, and little r, and little r, little r, little r, little r. Oops. It's just a random little r floating around. Little r, and he has to have at least one big R. Okay, but they have unaffected children who also have to be little r. Oops. Which means he has to have a little r as well. So he had to be big R, little r, because he has to have a little r to give to each child, and same here. She would have to be little r. And big R and little r come to this daughter to make her affected. Now, I just proved myself right, but now I get to look at that story. According to this Punnett square here, if you ran a Punnett square with that man and that woman, I should have a 50% chance that I have a child that's affected. And in 5 children, that's awkward. 5 children, no one's affected. It's not impossible. What are the odds of flipping a coin 5 times in a row and getting heads every time? So that's where you could be like, okay, I proved it right, but something's fishy going on. And so that's where you could reconsider and make sure there's no other options and then pick the improbable. Does that make sense? I suppose you can't really respond to me, huh? So yeah, that's how I go about it. So in this case, it met the rules for X recessive, and it met the rule of thumb, because I mean, I guess out of 3, I had twice as many men as women, but the rule of thumb didn't really hold there. Didn't really help very much at that point. But it met all of the rules of X recessive, and X recessive was more reasonable than any other option. So we went that way. Does that help a little bit? Let's come look at another example. Let's see. Oh, well, that's obviously Y-linked. Okay, let's look at this example. We have, let's see, let me see if I can bring in my rules here. Nope. Apparently I cannot. Let's go back and get them. Okay, here we go. The A-R-E-D. Okay, here we go. This one can't be Y-linked because, the Y, the M, because I have women affected. And the father doesn't give it to his sons. And it can't be mitochondrial because affected women don't give it to all of their children, and affected men give it to children. So these 2 are out. All right. Now we've got autosomal dominant, so now we have to ask, is it dominant or recessive? In this case, every affected child has an affected parent. That makes it dominant. Autosomal recessive, or autosomal, sorry, I'm tired. Okay, here we go. Autosomal or X-linked. In this case, if we count the number of women, I've got 1, 2, 3, 4 women to 2 men. That's twice as many women as men, which in this pedigree, that's pretty respectable. Now let's go look at our X-linked ones. So we're starting to lean towards X-linked because we already have, according to the rule of thumb, we're already having a suspicious quantity of women affected. If affected men pass to sons, it's a no-go. I don't have any affected men passing it to sons. So we're good so far. With X dominant, every affected man must give the disease to all of his daughters and none of his sons. There they are, 1, 2, 3. So in this case, we met rule 2 as well. In rule 3, every affected daughter must have an affected father. So it doesn't meet the X recessive rule, but it meets the X dominant rule. So with step 2, we filtered out the recessives as being unlikely. And in this case, it met the rules for X dominant, plus the rule of thumb seems to say it's X dominant. So we answer X dominant. Now, if I'm feeling a little scared to see if X dominant works, then come up with a story. This man would have to be X big R, X big R Y. She would have to be X little r. He gives the big R to all of his daughters and none of his sons, so they're all heterozygous. So she is now X big R, X little r. He is X little ry, because that's the only way he doesn't show the disease. And then she passes an X big R to him and an X little r to him, and an X big R, X big R to her, and on an X little r, so she's heterozygous and shows the disease. And an X little r and an X little r to her, and she's homozygous recessive and doesn't show the disease. Oof, I just proved myself right. Now let's say that we had decided it was X-linked recessive for some random reason. This is a better example to demonstrate step 4. We had decided it was X-linked recessive, then that would mean this man would have to have an X little ry, right? So let's presume that this is X recessive. Ding. Okay, there we go. This man would have to have an X little r and a Y. This woman would have to have an X big R, X little r, because I have affected daughters. So then she gives an X little r down here, he gives an X little r down here. All of the daughters come out X little r. And she could give her X big R to both of those sons, so far so good. Does that make sense? And then both of these sons get an X big R from mom, and a Y from dad, and so they don't show the trait. So we're good so far. Let's go to generation 3. This man has to be an X big R Y in order not to show the disease. For this son, he gets an X little r from mom, a Y from dad, and shows the disease. We're good so far. X big R, wait a minute. Shoot. Where's that big R coming from? The only one with a big R is dad. See how that caught us? At first glance, maybe this could look X-linked recessive. But I just ran into a barrier here where it's like, dang, in order for him to be not affected, he has to have an X big R Y, but that means he had to get both of his chromosomes from dad, and that's not kosher. This daughter also causes a problem because she has to be X little r, but wait a minute, where does the second X little r come from? Dad has an X big R. See how that starts to raise questions, and you're like, wait a minute, by doing step 4, I just proved myself wrong. So now I have to back up a step because I know I just did something wrong. So you don't have to do step 4, but it's a good safety measure. It takes a little bit, but it's a good safety measure. So feel free to walk through the rest of these problems. With this spreadsheet can be downloaded off of the week 9 page of the week 8 page of my website right there. It's got 21 practice problems. And when you get the wrong answer, so you select your answer from the drop-down list. And when you get the wrong answer, down here in the helpful hints box on each one of the 21, it tells you in the first paragraph whether or not it's possible, or whether or not it's possible but not likely, or impossible. In this case, X-linked recessive, we just proved it to be impossible, and sure enough, it says X-linked recessive inheritance is not possible for this pedigree. And then it goes in and tells you the rules for X-linked recessive so you can double check. Well, with let's come in here with one like autosomal dominant that could be possible. In this case, then it tells you that it could be possible, but there's a better explanation. So the first paragraph says true autosomal dominant inheritance is possible, but there's a better explanation, and then tells you the autosomal dominant rules. So each of these problems is designed like that. I've worked them all through so that I found all of the possibles and the most probable answer. And so the most probable answer will be marked correct, and all of the possible but not likely answers will be marked true, incorrect but true autosomal, or true, this inheritance is possible but, and all of the impossible ones will be marked incorrect and say it's not possible. So work them through and double check yourself, and you have a way to double check to see if it's possible or not likely, at least with these ones. Let me know if you have any other questions. Again, I'm sorry this is coming out so late. I sure do hope this helped. Take a swing at the practice exam. Let me know if you have any questions. And yeah, good luck.